For 60 years, the chip industry kept Moore's law alive through a simple strategy: make transistors smaller and spread them across a flat two-dimensional plane. But that horizontal expansion has hit a hard boundary. Designers are running into physical limits imposed by atomic dimensions and quantum effects. We cannot shrink components horizontally much further without the physics of the transistor breaking down. The new alternative is monolithic 3D integration. This is distinct from current commercial 3D packaging, which glues separately manufactured, thick chips together. Monolithic integration means building entirely new transistor layers sequentially, right on top of the existing ones. To keep computing power growing, engineers have to move past the two-dimensional land grab. They need to figure out how to build functional skyscrapers on a single silicon lot. But building vertically introduces a physical wall. If we look at a cross-section of a two-story computer chip, we hit a strict thermal budget constraint between the layers. Fabricating high-quality crystalline silicon for upper layers demands extreme processing heat, approaching 1,000 degrees Celsius. But if the delicate bottom circuitry is exposed to temperatures above 400 degrees, it will physically melt and break. For years, engineers assumed the only way around this was to use alternative materials for the upper tiers, materials that could be applied at lower temperatures. Because those low-heat materials had inferior electrical performance, the upper layers became weak floors in the skyscraper. Stacking vertically offered little advantage if the new floors couldn't process data as efficiently as the foundation. A breakthrough from the University of Illinois bypasses this thermal paradox by changing the fabrication sequence. They realized that high-temperature processing is only required to grow high-quality silicon. It is not required to stack it. Instead of growing silicon on top of a finished chip, they prefabricate single-crystalline silicon nanomembranes. These are sheets 10 nanometers thick or less that already possess perfect crystalline structure before they touch the actual circuit. Using a roll transfer printing process, the team applies these flexible silicon membranes directly onto a completed circuit layer. The bonding requires a maximum of just 200 degrees Celsius. By treating silicon as a flexible, pre-processed skin, the engineers avoid the 400-degree destruction limit, allowing vertical construction to proceed safely. Making this ultrathin layer functional without heat requires junctionless transistors. Let's compare a standard transistor to this alternative. Standard transistors rely on high heat doping exceeding 600 degrees Celsius to activate specific regions after placement. But a junctionless transistor is uniformly doped before layering. Because it's so thin, it needs no hot processing once on the chip. The laboratory metrics proved the concept. They achieved sub-10 nanometer alignment between tiers, processed safely under 400 degrees, and hit device yields of nearly 100% across 3 stacked tiers. By redesigning the transistor to match the ultrathin membrane, they successfully stacked high-performance silicon without melting the existing floors. If monolithic 3D integration reaches commercial manufacturing, it shifts chip design from a flat layout geometry problem to vertical architecture optimization. Stacking logic blocks sequentially creates an environment where vertical interconnects linking layers are 10 to 100 times denser than conventional 3D packaging. Physically stacking compute layers directly on top of memory layers drastically reduces data travel distance, widening the communication bandwidth between components. This vertical proximity addresses the data transfer bottlenecks currently throttling advanced AI workloads. Bringing compute and memory physically closer together completely removes the latency of sending signals across a sprawling, flat chip. However, this process is currently a laboratory demonstration. High-volume commercial manufacturing remains unproven, and the scale-up barriers are significant. The physical challenge is scale. Proved on a 75mm research wafer, transferring flexible membranes perfectly across a massive 300mm industrial wafer is a severe engineering hurdle. Also, packing active devices vertically introduces a concentration of trapped heat deep inside the 3D stack. The demonstration suggests the barrier to 3D chips was the timing of the heat, rather than the silicon material itself. The final test is whether this decoupling method can survive the brutal physical and economic realities of massive foundry scale.